Hello, and welcome to this online training on Intel Simics Simulator for Intel FPGAs command line interface. Feel free to pause, move forward, or go back as you need during this presentation. At the top right of the presentation, you will find a list of helpful links and resources on the subject. Let's get started. The Intel FPGA portfolio supports this transformation, including discrete and integrated FPGAs that are expected to improve processing efficiency, task specificity, and connectivity. Intel FPGAs can provide a variety of workloads in network processing as well as compute and storage acceleration. FPGAs are mass-produced, standard product ICs that can be reconfigured in the field to accelerate virtually any digital algorithm. They offer greater throughput, execution speed, and energy efficiency than CPUs on computationally intensive parts of algorithms, but with the ability to adapt quickly to changes in algorithms, data patterns, or performance needs. They can be reconfigured in the field to accelerate virtually any digital algorithm. They are available in 5 current families: Max, Cyclone, Aria, Stratix, and the newest family Agilex, all with increasing capacity, performance, and feature sets. The objectives for this e-learning are to provide an overview of the advantages and functionalities of Intel Simics Simulator for testing, development, and analysis during the whole product lifecycle from conception to conclusion. To understand the Intel Simics Simulator command line interface and simulate a model for Intel FPGAs hardware for different applications and test cases. These are the topics that will be covered in this e-learning. Introduction to Intel Simics Simulator for Intel FPGAs, project creation and simulation setup, Intel Simics CLI and examples, demonstration of Intel Simics CLI. The Intel Simics Simulator for Intel FPGAs is a full system hardware simulator for testing and software development. One of the advantages of using Intel Simics is that you can target the simulation to support the early software development process of a product lifecycle since it can run unchanged binaries. Intel FPGA devices often integrate a mixture of components including one or more than one CPUs, soft or hard, in a single package. Each of these CPUs can require its own firmware and software integrated by several layers of infrastructure that include things like bootloaders, drivers, operating systems, and applications. Use the Intel Simics Simulator for Intel FPGAs to test your application and its interactions with all these layers. To download the Intel Simics Simulator, you can go to the link provided in the resources section for this presentation. Intel Simics Simulator for Intel FPGAs provides with an environment to speed the development process due to its capabilities and what the simulator can do throughout the product lifecycle. Some of the features include hardware inspection, software development, dynamic system configuration, hardware modeling tools, scripting, test application and its interactions, debugging, continuous integration and customer enablement through shorter development cycles. Throughout the life cycle, you can have access to the earliest product architecture and design evaluation through the hardware model to enable testing and hardware inspection. You can also test firmware developed and model customer systems. The features for Intel Simics Simulator for Intel FPGAs include use cases. These are used for a variety of virtual platform-related tasks: pre-silicon embedded software, bootloaders, drivers, and user application, development, verification, debugging and continuous integration, and customer enablement. CPU architectures. The model support for Intel FPGA devices, ARM processor architectures are supported. Modeling and languages. The simulator provides industry best-in-class support for System C. Models and extensions to Intel Simics Simulator can also be written in C, C++, Python. Performance. You can boot to Linux or Zephyr prompt in just a few minutes, allowing interactive use of the virtual platform. The simulation engine in the Intel Simics Simulator is multi-threaded, allowing processor models and other parts of the simulated system to run in parallel. Scalability. With optimizations to how memory and disks are managed, very large disks and memory sizes many times that of the host can be easily simulated. Large networks of hundreds of target systems can be simulated. Integration. The integration of detailed processor architecture models, memory system and cache models, physics models for embedded hardware, networking models, and more. Automation. The Intel Simics Simulator supports automation of target systems and target system software using scripting. Debug support. You can debug of software using symbols files, C++ debugger, full hardware inspection with all devices and register names, step-by-step execution, trace generation, advanced breakpoints and connection to remote debuggers such as GDB and the risk-free debugger in Ashling risk-free IDE for Intel FPGAs as you would do with the hardware. The Intel Simics architecture has the simulator infrastructure and the user interface to work with the simulation of hardware and test software applications. The Intel Simics core provides simulation services through the Intel Simics API. The Intel Simics API offers a large set of functions that are used to interact with the simulator. This includes configuration management, simulation control, running, pause, breakpoints, HAPs, checkpoints, scheduling, time and event handling, logging, memory operations, module loading, multi-thread and scaling, file access, processor operations and cache operations. The target software is what needs to be tested during the simulation. It normally is integrated by several layers of software that include drivers for making use of the hardware components in the target system, bootloaders, operating system and applications. The target system hardware is the real hardware specification over which the target software can be executed. From the target software perspective, the model must accurately reproduce the behavior of the real hardware. On the right, you can see how to use the target system hardware for debugging, testing, modifying or configuring each element. Some of the terms that describe elements that Intel Simics works with are target script. This script defines the configuration parameters, runtime commands, instantiation of the hardware model components, and any network configuration. It is a .simics file. Target system. A target system is sometimes referred to as a target machine. It is the hardware that will be simulated. Virtual platform. A virtual platform typically includes a model of the processor and any peripheral devices that the processor accesses. Device model. A virtual platform typically includes a model of the processor and any peripheral devices that the processor accesses. This is the software that is simulating the functionality of the hardware component. The virtual platform architecture instantiates the components that integrate it and define the parameters values for any of the modules that integrate the target system to be simulated. The architecture also includes the runtime commands used to configure the simulation and control the flow. The FPGA component is related to the FPGA device that is being simulated. This may instantiate the FPGA fabric, soft CPU, etc. The board component represents the model of the board, PCB. It instantiates the FPGA component and all board-level components, SD card, QSPI memory, etc. The system component represents the complete system of the virtual platform, and this instantiates the board component. As expected, you can instantiate any component that is not part of the board in the system component. This may include other boards. In this diagram, you can see the steps to start working with Intel Simics Simulator for Intel FPGAs. The first step is to install the simulator. To refer to installation and download, you can go to the Resources section in the presentation and follow the link for setup. Everything needs to be installed in a Linux OS environment. The focus of the following slides covers the project creation after installation and the simulation setup. Deploying a virtual platform initializes the Intel Simics project directory as an Intel Simics Simulator workspace and copies all the files required to enable the virtual platform to the Intel Simics project directory. These files can include .simics scripts, Python components, DML models, and documentation. You can create the project following these steps. A. Create a project folder inside the directory for Intel Simics install. B. Deploy the virtual platform in the project directory. C. Customize virtual platform, if applicable. D. Build virtual platform using Make. After the virtual platform is built as described in the previous slide, then you can start to use the command line interface. To get started, you can use any of the arguments provided in the table or in the user guide. There are two ways to start the simulation. You can do it directly with the Intel Simics CLI or through Ashling RISC-free IDE for Intel FPGAs. The binaries added to the simulation project directory are the ones you would normally develop to test with hardware for booting. This includes generating an image and booting from a selected device, .wic, .bin, .image files, etc. To start the simulation, you can use any of the script files available in the project directory. For example, the first command can be used as /simics agilex 5e universal.simics. This launches the simulator and the target script. In this case, Intel Agilex 5 SoC FPGA is being targeted. This is an example of use of the binaries previously generated and being specified in the script file to test with the virtual platform. The SD image and the first stage bootloader files are defined in the target script. .wic file and .bin file. As noted before, the generated files that you would normally test in hardware need to be declared in the script to set up the simulation to allow the simulator to start the virtual platform with these files and run the Intel FPGA. Inside the Intel Simics Simulator, you will find three windows to work with. The Intel Simics Simulator graphic user interface, where you can start, stop simulation, debug, start with a new script, among other functionalities and tools. The Intel Simics Simulator CLI can be used to control the flow of the simulation. You can enter Intel Simics commands to interact with the simulation. The serial console for the device. You can use it as you would normally do with the hardware, reboot, add device drivers, configuration, etc. The system component represents the complete system of the virtual platform. In this virtual platform, this only instantiates the board component. The hierarchical name of this component in the virtual platform is system. The target script instantiates the system component, system, provides the CLI runtime commands, creates the network configuration, and defines the user configurable parameters that are propagated to other components when they are instantiated. The runtime commands in the target script include displaying some system information such as objects, memory map, status of the CPUs, status of the system, board, FPGA and HPS components, as seen in the slide. The CLI allows the user to control the flow of the simulation. With CLI, users can create and configure the target system, obtain an installation version, start, pause, and stop the simulation, inspect the status of the target system, debug target software. To obtain information about the version of Intel Simics, you can type in the CLI the command, version. This will display a table with a summary of the packages installed. To run and stop the simulation with the CLI is equivalent to doing it with the hardware. You can also add a running state with a limit of time and then stop. The command step I can be used to indicate the number of steps to show in the CLI of an instruction being executed. If you want to autocomplete a command, you can use the Tab key. To retrieve the command's history, you can use the up and down keys. The Help command is useful to search a topic with a word or by topic. You can define a variable and use the following operators: basic math operations, modulo operation, percentage, bitwise operation, C-style, comparison, string concatenation, and string formatting. Using Simics Simulator, CLI variables can be helpful when creating scripts to automated sequences of actions. Here are some examples of the use of output radix command to convert between variables. The variables can hold any type of value including Boolean, integer, float, string, list, or a combination of them. You can use the echo command to show the value of a variable, or to enter the variable at an Intel Simics CLI prompt. This demo includes the step-by-step to set the project and deploy the simulation for the target system, which is Intel Agilex 5 SoC FPGA in this case. These steps are done after the setup for Intel Simics Simulator for Intel FPGAs has been installed in the Linux OS host. To start the simulation, you must create a project directory inside the Intel Simics installation folder, then open the Linux terminal to start the simulation and setup. Now go to the directory created for the project inside the Linux terminal. In this case, it has already been created as My Sim Project 1. Then use the Linux terminal to deploy Intel Agilex 5 SoC FPGA target device. As you can see in the Linux OS terminal, the command for deploy is being used, followed by make. As covered in the slides, the command deploy is used to deploy a specific virtual platform, initializing the current directory as an Intel Simics Simulator workspace and copy all the required files to the directory. These are the components needed by the virtual platform and the target script itself. There is already a folder with the binaries created for this project targeting Intel Agilex 5 SoC FPGA. Right now we see that the SM Images folder contains the necessary files. The .simics file needs to be opened to indicate in the script where those files are located. For this, you can use Emacs as seen on the screen, or you can use any other text editor. Once the file is open in Emacs, you can add the SD image file for booting and the first stage bootloader locations. As we saw in the folder previously created, they will be added from the SM Images directory with the name for each file as part of the modified script. This will allow Intel Simics Simulator to start the hardware simulating how any other device will do it. The covered steps up to now are to set up the simulation and project. Now in the Linux terminal, Intel Simics can now be launched. This will start the simulator with the targeted device and the binaries necessary to boot. Intel Simics works as you would expect hardware to work. After the work of setting up the binaries is done, save the changes and move to the Linux terminal. The following steps will allow to get started using the simulated hardware. You can use the Simics command line interface to complete tasks including the following actions. Create and configure target system. Getting the installation version. Starting, pausing and stopping the simulation, which is equivalent to starting, pausing, and stopping the target system. Inspecting the state of the target system. Debugging target software by setting breakpoints and trace points. The Intel Simics Simulator CLI is always available, regardless of how you start the Simics simulator. When the simulator is started along with the Simics graphic user interface, you can access the Intel Simics Simulator CLI from the menu tools and then select command line window. Now that you know the functionalities of the CLI, we will explore more of the simulator too. You will see that there are 3 windows open: the graphic interface, the Intel Simics CLI window, and the serial console for the targeted device being simulated. Once the Intel Simics Simulator has started, the CLI will become available. As you see here in the serial console for the target, the system is booting. This might take a few minutes. Once the system has started, you will see the Linux OS prompt as you see it when the hardware has booted. A file can be created to go back and take a look at the results of debugging session or just the history of Intel Simics CLI. Let's take a look at a couple of examples of use of the CLI. Run or stop can help you run the simulation from CLI using the scene commands run or stop directly in the simulator. To start the capture by using the Start command line option, this will create a file with the given name. Use the command version to display the information of the version for Intel Simics or use the help options. Now for the use of list objects. Remember that you can use Tab key to complete the commands. Change the output of a value for a better view by using Output Radix option. End the command line capture by using Stop command line capture. Now the file has been saved with the changes and capture of the Intel Simics CLI. Explore many other options and capabilities of Intel Simics Simulator and CLI in the user guide link provided in the resources. Now that we have Intel Agilex 5 SoC FPGA booted to the embedded Linux OS, we can say hello SoC FPGA, as we will do it using the actual hardware. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5 minutes quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live, instructor-led course presented either in person at an office local to you or virtually over the web. All instructor-led courses have hands-on labs exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages, called landing pages, dedicated to specific FPGA technology and high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. This concludes the training. Thank you and have a good day.